Hi everyone, hope you are doing fine. So in this video, I am going to solve the path existence queries in graph 2 problem. In previous video, I solved the first version of this problem. So let's see how we can solve this second version. So if you have not solved the first version, you can watch my previous video in which I solved this first version. Let's start it. So in this problem, we are given a and nodes and labeled from 0 to n minus 1, and we are also given an integer array nums and a max difference. So undirected edge exists between node I and j if the absolute difference between their nums value is going to be a at most max difference. So like this thing is exactly same as of first problem, but the only thing is like in the previous problem while querying the while solving for the queries we have to return whether they belong to the same components or not. But in this problem we have to return the what is the minimum distance between these two nodes. So let's take the example to better understand the problem. So in this problem, let's see. We have n is equal to 5, and we have nums array and max difference of 2, and we have to solve for this query. So let's firstly make a graph from this, like how the graph will look something look for this. So we have something like 5, 3, 1, 1, 9, 10. So in previous case, like this thing this nums array was in sorted order, but in this case it is not sorted. So we have to firstly sort the array. So we instead while sorting we have to make the pair, like for which node this is the value for, like one is for the second node, then three is for the first node, five is for the zeroth node, and the ninth is for the fourth node. Nine is for fourth node, and 10 is for the fifth node. So we'll look something like that. So after making the graph, what we have done is then we have firstly, now let's make how we are going to make this graph. So like if the difference between these values are going to be less than equal to difference, then they belong to same components. Let's say for the uh like can this 2 and the node belong to same components? So yeah, let's see one is its values 1 and 3. 1 and 3, the difference is going to be a 2, so it's belong to same component. So graph will look like something like this. Then we have 5 comma 0. 3 and 5 difference is going to be 2, so they belong to same component. But you can see difference between 9 and 5 is going to be greater than max difference, so they belong to different component. So we have something like 9, and we have something like 10. So yeah, so our graph will look something like that. So after that we have to query for the different so we have to answer the query for different types of we have different types of query, and we have to solve the we have to return the result for that. So our first query is like we have 0 comma 1. So what is that 0 comma 1? So how we get the value for 0? Like what is the value for 0? You can see the 0, the value is going to be 5. So this is the for 0. Like if we are solving for 0 comma 1, so 0 the value is going to be a 5, and for 1 the value is going to be a 3. So we have to check whether the 1 and 3, sorry, yeah, for 1 the value is going to be a 2, sorry, not 3, the value is going to be a 2. Not 2, I think it's a 3, like it's a 1 comma 3, so it's not 2, it's a 1 comma, we can say 1 comma 3 comma 5 and 9 comma 10, yeah. So it's a 1 comma 3 comma 5. So for 0 it's going to be 5, and for 1 it's going to be you can see for 1 it's going to be a 2 value. Oh sorry, for 1 it's going to be a 3 value. So this is the index, and this is the value, like actual nums value. And so we are given something like we can say index, and we have to get the value again, so we can simply get this value. So it's for 1 it's going to be you can see 3. So we have to check whether what is the minimum distance between 3 and 5. In previous problem, but we have to simply check can they belong to the same component, so we are using disjoint set union to check. But we can't simply do something like that in this like in this problem, because if we are going to traverse the distance, then it's again going to be a big of, and like for, like because we get like this thing belong to this same component. If they belong to same component, it mean that like there exists a path and we have to find. So to find the path, we have to traverse from 3 and move until like move to next parent, or we can say next child, until we get the 5. So in that way it's going to be a, like big of n for every query. So like can we do something better in this better for this thing? So yeah, let's try to solve it in a like better way. So for now we are skipping this thing like indexing, because we can simply get the index. So we are skipping it while from now I am going to skip this part, like index part, only taking this value, because we can simply maintain a like a array, and then we from that we can get the like we can maintain for what index, like for 1 the value is 3, for 0 the value is 5. So yeah, we can get that thing. So yeah, let's see how we can do something like this. So like after sorting the array, our array will look something like that: 1 3 5 9 and 10. So like what is the maximum we can achieve from, like what is the maximum we can reach from this index? What is the maximum? So we can reach from this one, we can reach up to, give the indexing to it: 0 1 2 3 4. This is going to be a 3, this is going to be a 4. We can reach up to 2. Sorry, we can, yeah, you can see we can reach up to, from 0 we can reach up to, sorry, 1 only, because the difference between 0 and a 5 is going to be a greater than that. So from like in a one step from 1 we can only reach this, no this index only up to 1 index. So similarly for these 3 in one step we can only reach up to 5, so it's going to be 2. From 5 in one step where we can reach, we can't reach anywhere, because we can't reach 9, because its difference is not less than max difference. So their difference should be less than max difference. In this problem the max difference is 2, and the difference between 5 and 9 is going to be 4, so we can't reach like this node 3. So from 3 we reached up to 4, and from 10 like 4 we also reach up to 4. So we are going to make something like this, we can do something like this for what is the maximum we can achieve in one step. So again we can see, like if we have to reach from 1 to like we can reach up 1 in, like if we do one step, like what is the maximum we can reach if we do we can take two steps. By two step I mean that we can reach to what is the maximum like index we can reach by taking something like middle value. Let's say if we reach from if we reach 1 3 like 3 and 5 in a one step, like in a one step, from these two value what is the max we can achieve later on in a second move. So what is the maximum we can reach in a second move? So it's going to be a, like in one step what we can go, like in one step we can go to 3, and in again in we can take one step from this, so it's going to be a max of 2. So now from what is the 3, what is the maximum we can reach in two step? Like in one step we can reach to 5, but in from 5 we can reach up to max 2, so it's going to be a only, we can say 2. Similarly for this 5 we can reach only up to 2. So from 4 in one step we reach to 4, and in second step we can also like we can't move do anymore. So yeah, that's it for this. So in now let's see what like for three moves. By three moves we I mean that we can like firstly jump to one like one index, and then again from one, and then reach to final. So from one we can max reaches, like in one step we can reach to 3, and then we can jump from 3 to 5 in 2, and then again jump. But from 5 if we jump again jump from 5, what is the max we can jump? we can jump up to 2 only. So again it's going to be 2. Similarly for this 2, it's again going to be 2, 2, 2. So we are tracking, we are doing something like this. But if we are going to do this for like another, like because we can do and like and step, like if we have something like we have to reach, we have query like 1 to 10 raised to power 5, like say it's a max range, and we in each step we can do max of one jump. So in overall it's going to be, we can say it's going to be 10 raised to power 5 iterations. So we have to do this for 10 raised to power 5, and each iteration we have to completely traverse the array. So it's going to be very high. Can we do something better to do this thing? Like if we have done this thing, we can simply check like we have to, let's say we have to something query like 1 comma 9. Can we achieve one, like can we go from 1 to 9? We can check what is the maximum, like for like let's say it's going to be n, for n it's going to be same only. For n, can we say that like for like we have to go to n 9. We can check for can we reach to max of 9. Can like from 1 can we jump, if we jump n step can we reach 9? We can't reach 9, like we can reach only 2, so we can take this 2. So now we can reach this 2 to in how many steps? We reach this 2 to in n step. We reach this to n step. So we n is calculated to our answer. Now from n we have to go like where we have to go. From n we can go up to, we can say something like from n like 2, we are at 2 position like this. From 2 in n step where we, like in n minus 1 step where we can go, like in this only we also go up to 2. So after that we are going to stop. So yeah, so you can see the max we reach is 2, but we have to reach a value of 9, so it is not possible. So we can break, like we can break this thing. So you can see we have to answer again, for answering the query we have to do n step. So like this is very inefficient. So can we do better than this? So like so this problem can be solved with the help of binary lifting. If we you have here about this thing like binary lifting. Binary lifting. So what happen in binary lifting? So instead of calculating for every, like we are calculating for every k equal to 1 to n. So we calculate k for only powers of 2, like 2 powers of 2, like for 2 raised to power 0 is 1. Then 2 raised to, we calculate for 2 raised to power 1, which is going to be 2. Then 2 raised to power 2, that is going to be a 4. 2 raised to power 3, that is going to be a, we can say like 8. 2 raised to power 4, 16. 2 raised to power 5, 32. So you can see like we are moving our like moving in a double thing. So if we are moving something like double, like n into 2, so it means that we can divide n by log n. So that log n, so if we reach from n to 1 in a log n, so the time complexity is going to be do like we have to only maintain the log n entries. Because like if we have only 10 raised to power 15 value, if we do 10 raised to like 2 raised to power 18. So if we do 2 raised to power 18, you can see the value is pretty high, like it's greater than 10 raised to power 5. So yeah, so we can iterate only up to 2 raised to power like 18. So we have to maintain only 18 entries. So like how, but how it is work, because let's say we have something, a number like 11. So in binary, 11 can be represented as like 1 8 plus, we can say 0 4 9 10 11. So you can see like it's going to 2 raised to power 0, it's going to be a 1. 2 raised to power 2 is going to be a 4. 2 raised to power 3 is going to be, we can say 8. 2 raised to power 4 is going to be a, oh sorry, oh yeah, 2 raised to power 1 is going to 2. 2 raised to power 2 is going to be a 4. 2 raised to power 3 is going to be 8. 8, but for this 4 we have 0. So like you can see like in powers of 2 we can represent any number. So let's say if we have calculated the answer for, let's say how we can calculate the answer for 2 raised to power we have something like 2 raised to power 16. So 2 raised to power 16 can be represented at something like that. 2 raised to power, oh sorry, 2 raised to power 4, sorry, I have to represent 2 raised to power 4, not 16. So 2 raised to power 4 can be represent something like 2 raised to power 3 plus 2 raised to power 3, something like that, because 2 raised to power 3 is going to be 8. then 2 raised to power 3 is going to 8, again it becomes 16, which is equal to 2 raised to power 4, 16. So if we have calculated something answer for like we have something like 2 raised to power 16 for the, like if we have to calculate 2 raised to power 16 for this answer, like this value, but we have already calculated 2 raised to power 3 for this, so we can take 2 raised to power 3 and again move to 2 raised to power 3, and from that we can get 2 raised to power 3, so we get the final answer. So let's see how the binary like how the binary search will work. So for to explain the binary search, firstly let's understand the binary search in detail, because this problem is like if you know binary search, this can be easily done. So let's understand the binary search. So to understand the binary search, I am going to explain the standard problem name as we can say ancestor, like we have to find the ancestor of the tree, kth ancestor. So yeah, let's say we have some tree something look like that. Let me also give a value to node 3, 4, 5, 6, 7, 8, 9, 10, 11. So yeah, this is the tree. And now let's say we have to find the, for 10, like 10th node, we have to find the like kth ancestor. By kth ancestor I mean, like you mean simply like you have to do that like that parent, like you can assume this is the first parent, this is second, and this is the third. So we have to find the kth parent. So let's say k is 3. So in that case, the its third parent is going to be a 1 only. So but instead of calculating by every move, so what we can do, for every node we can calculate the answer for answer in the power of 2, like let's say we start from 0. Let's try to build this, we can say this array for the, we can say binary lifting array. So in binary lifting array we maintain, like we calculate for the k values, and after that we can for other answer we use that to again calculate that thing. So let's assume we have something like this. Yeah, we only, because we have only like four the depth of 3 is like very less, so we not need much like power of k. So it's a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is k is equal to 0, k is equal to 1, k is equal to 2, k is equal to 3, k is equal to 4. So we have something like, by k equal to 0 we mean that it's our parent, like it's immediate parent. For k equal to 2 we mean that it's immediate parent. So what is the immediate parent of this node, like node 1? The immediate parent of node 1 is -1. So what is the immediate parent of 2? 2 parent is 1. Similarly, the 3 parent is also 1. 4 parent is 2. Fifth parent is 2. Sixth parent is 3. Seventh parent is 3. Eighth parent is, we can say, this is going to be 4. Ninth parent is again 4. 10th parent is going to be 5. So yeah, let's again, so remove this part. So we can remove this 11th node for now. So we have something like that. So now how we can calculate the answer for k equal to 1? Who is the k 2 raised to power kth child? 2 raised to power k, what is 2 raised to power 1? 2 raised to power 1 is 2. So who is the second child of that, like a second parent of that node? So who is the second parent of 1, like for 1? For 1 we are going to say it's going to be again -1, but for second we can calculate, we will try to calculate. So to calculate, we'll like I already explained, like we can represent 2 raised to power 4 as 2 raised to power 3 plus 2 raised to power 3. So we can, like we have to only calculate this for 2 raised to power 1. So 2 raised to power 1 can be simply written as 2 raised to power 0 plus 2 raised to power 0. So firstly we can calculate the, because for 2 raised to power 0 we have already answered, because like if we do something like we are calculating for dp of like k comma I. So k of I, dp of k comma I can be written as something like dp of, how we can calculate, we can do k we can simply calculate k minus 1 comma, like we remain, because for this we have already calculated, because firstly we are calculating for k equal to 0, k equal to 1. So what is the value for k, like for going to k equal to 1? K is equal to 1 and I is equal to 2. So value is going to be a k minus 1 means 0 comma 2. So what is the value of 0 comma 2? It's going to be a 1. So you can see we can, in one step we can reach to, if in k raised to power 0, k raised to power 1, like one step we can reach in one, this node, we can say node 1. This is the node we can reach. If we reach node 1, again we have to make a 2 raised to power k minus step jump. So if we again made, what is going to be for this, it's going to be a dp of this, dp of, so after all our, like, so to calculate the complete answer, the our dp state will look something like, so let me write here, so it will be, like I can easily write here. So dp of k minus 1 comma I, something like that we can say. So you can see, like, if we are at, something, like if here, like, k equal to, we can say k equal to 1 and the I is 2. So we can simply check what is the answer for k equal to k minus 1 comma I. So what is the answer? Answer is, like, we can reach to node 1, like it's a, like node 1. From node 1, like what is the value of dp of this, going to is a 1, like I, like I is going to be this, sorry. So like I is going to be this, so it will look something like this, we can say. And k minus 1 is going to be same, because sorry, oh, so I, like, write the wrong formula, so let me again write this thing. So the formula is going to be, let's say, we are at dp of I comma k, we are calculating for dp of I comma k. So how dp of I value is going to be a dp of, like, I, like, for, firstly we have to do I comma k minus 1, and then again we have to do, like for this we have to, if we know reach to know that, that node, again we have to get the answer for k minus 1. So what in this case, we reach to, minus 1, because you can see, like, the second parent of the, 2 is node is going to be minus 1. Similarly for 3 it's going to be minus 1. And for, like, yeah, now for 4, what, like now for 4 you can see how we can calculate for 4. Let me make this a little bit smaller. So we get, like we, now we get our formula. Let's, see how we are going to get this answer. So like dp of I, what is I is going to be a 3, sorry, I is going to be a 4 and k is going to be a 1. So it's going to be a dp of, what is the dp of I comma k minus 1? What is this I is 4 and k minus 1 is k minus 1, 3. Like we get this one value, like dp of I is 4, k minus 1 is 0, and this k minus 1 again is going to be 0. So what is the value of this 4 comma 0? Like I is 4 and k is 0, so value is 2. So it's going to be a dp of 2 comma 0. So what is the value of dp of 2 comma 0? dp of 2 comma 0 is going to be 1. So for this the answer is going to 1. So you can see, you can also manually see, like for this graph node 4, the, second parent is going to, first parent is 2, second parent is going to be 1. Again we will try to fill like similarly for this 5. Again we get answer as 1. For this 6 we get 1. For the 7 we get 1. But for 8, let's say again we say calculate it. For 8 we can simply go from its previous child, like its previous value is going to be a 4. What is the 4 zeroth value? 4 4 node zeroth value is second, so we get here second 2. Similarly for 9 it's going to be 2, and 10 it's again going to be a 2. So now again we get 2 raised to power k equal to 2. Now 2 raised to power 3 is going to be a 4. Who is the fourth node for this? So for again going, so we can skip for 1, because for 1 all the parent nodes are going to be a -1. So let's calculate for second. So for second, what is going to be value? From formula if we get, it's going to be a like uh, k is 2, and like I is 2 and a k is 3. Okay, is also 2, not 3, k is 2. So dp of 2 comma 2. So dp of 2 comma 2, let's define here value again, so we can erase this previous value. So dp of 2 comma 2 is going to be a dp of, what is the value of I comma k minus 1? I comma k minus 1. What is this I? It's going to be a dp of, what is the I value is going to be 2, k minus 1 is going to be a 1. So dp of 2 comma 1, dp of 2 1 comma is -1. So we can also write some condition, like if the value is already -1, we know we don't need to check for like it's, because if we pass -1 in this index, it's going to give a like, because there is no index like indexing -1 in a array. So we can, because if for -1 we can reach -1. Again for this, again it's going to be -1, because for 3 there is no 2 raised to power 3 child, because for every node you can see like there is no fourth node for like fourth, like this is 1, this is second, this is 3, third node, so no fourth. So again for this -1, it's going to like for again for k equal to 3, like again it's going to be 8 like, because there is no eighth node, again we can say this is going to be -1. So I am simply marking this. So like this all value are going to be -1, this -1, and this also -1. So now let's see, if we are at node 9, we have to calculate the k equal to 4 child, sorry, k equal to third child, and we are at this node 9, node equal to 9, and we have to calculate the third child. So how we can calculate? Because you can see we don't have any value name as 3, because for like if we can't make directly k jump, because this value in actual, this value is going to be a we can say 1, this is going to be 2, this is going to be 3, this is going to be sorry, this is 4, 8 and 6. So we can traverse from like previous direction, like if we can make a 2 raised to power k jump, we can't make 2 raised to power 4 jump. Can we make 2 raised to power 3 jump? Can't make. Can we make 2 raised to power 3 jump? Can't make. Can we make 2 raised to power 1 jump? We can make, because if we at k equal to, we have to find for k equal to 3 and its value is k equal to 2. So we can make a 1 jump. So like if we can check for like its answer is like node is going to be, we have to find the parent of node equal to 9. So then node become like, we can make jump from node 9 of 2 jump. If we take for node 9, take a jump of 2, we reach to second node, like because 1 jump, 2 jump, so we reach to node 2. So this become node 2. Then from node 2, what is the left remaining k? From node 2 we have to make a jump of 1. So again, because we check for 1, can we make this 1 jump? Yeah, we can make 1 jump. So if we can make 1 jump, you can say like, who is the like parent of this node? Who is the parent of 2? The parent of 2 is 1. Oh, sorry, like you can see the parent of 2 is 1. So we reach to 1. So for k equal to 3, we get our answer as 1. So like this is the way we can like you can do to solve any binary search binary lifting problem. So if like this is like in if you try to understand, it's a pretty tough thing. But if you understand this, you can dry run to understand it in a deep way, like a deep way. So if you once understand, then this formula is a very pretty, like a very easy formula. And if you forget this formula, we can you can easily drive, like if you know, you can represent some number like this, so you can simply drive this formula on the go when you are solving the problem like this. So yeah, let's see now how, so now instead of in this in our like a problem, so we are calculating for 1 equal to like n. So instead of doing for this, we can simply calculate the value for n equal to like k equal to 0, k equal to 1, k equal to 2, 3, and like up to log n. So let's see the code, how I solved it in code. So firstly, I am declaring a T array where I am adding the like a value nums of I, I change the nums to a v, so v of I value, and then I have added I to it. So after that, I am sorting T. So like if we you don't pass pass a 2D array and don't pass comparator, so it's it's sorted on the base of first value. So it's get sorted on the base of first value. So after that, I am creating a making a get value get value vector. So because for answer we have to get we are not because we get only node. So to get the actual value, I am making this value. So for every index, I am storing the I value here. So instead of doing something like this, you can also I think you can we can also do something like here only. Get value of t, it's going to value of I is going to be a, no, we can't do something like that, because the array after sorted the array, the value will changes. So after that, I am declaring a dp array. So like in our case, up to 17 is also I think the because the value in this the constraints are 10 to the power 5, so we can easily represent 10 to the power 5 number in 17 bits. So we can only do something like for 17 only. So but for safer side, I have add a value of 20. Then initially, then firstly, I am doing how, like from first node, what is the maximum I can reach. I am checking if the right is less than I, it means that I can't reach the further further nodes. Then I am making the right as I. And then I am checking if right, if the right plus 1 is less than n, because if the it's not part like the last node, because we can't check for last node. If it's not last node, and I am checking if the right plus 1 comma 0 minus t of I comma 0. So if it's less than we can say max difference. So it's something like this, like I already explained this thing. So yeah, so if I am at this node, after sorting, our array will look something like this. Yeah. So I am at this node, I am trying to check if this is a I can achieve move to this node. Yeah, I can move, but I can't move to this node. So for that, because the difference is going to be a greater than dot. So I am checking if the right of I plus 1 is going to be a less than equal to max difference, then I can move to that node. If not, then right will remain as same. So I am assigning that dp of I comma 0 to right, because from in 0 step we can reach, because for 1, 2, and 3 we are calculating. So it's k equal to 0. For k equal to 0, we are already filled using this array, and after that we are going to calculate. So yeah, we are assigning that value. So now how we calculate for another value. So it's a simple we in one jump we can reach to max of this. In if we take two jump, we can reach to its previous value dp of I comma j minus 1, and then again we do j minus 1. The formula, this is exactly the same thing I have done here, and this is also the same thing. So you can try to dry run these things, then you will clearly get what we are doing in this. So yeah, so I think that's it. That's it for the binary lifting part. So I am traversing from a 0 to, and I am checking what is the maximum we can go in a k step. So after that, I am simply traversing the query. So, but to get the actual value, I am making that call to like passing the query zero value and a one value to get the start and end. So if the start and end are like start is greater than end, I am swapping the value so that start must always be a less than end. And if the both values are going to be the same, then it means that there is it is the same node. In that case, our answer is going to be a zero. And then I'm continuing this loop to move to the I like next I. Then the current is going to be a start because we are starting from start. And after that, like if I am in a start, I am traversing from j equal to 17. I am checking if I can make k jump from this like this current node, like from start. If I made k jump, and if I am less than end, then I am making that jump and again adding the steps as 2 raised to power k. So 2 raised to power I j jump, like if I am making 2 raised to power j jump, 2 raised to power j jump. So this is a simple like like you can also use something like 2 raised to power uh like power of 2 raised to 2 comma j, but this is a simple like a bit like a bit like we can say bit technique to calculate the 2 raised to power I. So it's like something like one left shift j step. So if you do like we have something like 0 0 0 0 0 0. So if we do j left like one left shift by j step, j is 2. So again 1 2, so 2th bit become 1. So 2 raised to power 1 is going to be a 2. So like we get 2 value, something like that. So then I am checking like if at the last like dp of value is going to be end, then I am adding steps plus 1 to our answer. And else because it's not possible, so I am adding minus 1. So at last I am returning answer. So you can see in this case we are handling this minus 1 case thing. But in this case, because this change is according to problem, so I am not like I don't assign the value. If you don't assign value in a vector in C++, it's get assigned to 0. So like we are assigning the value of 0. So as we have assigned the value 0, so the max end can be a 0. So it's always going to be less than that. So in that case, we are returning like minus 1. Else we have to like explicitly check for like in every place, in this place, like if it's not minus 1 again in this case. So that become a like hectic thing. So yeah, I think you understand the problem. So let's try to run this problem. So you can see like this is working. So let's remove this console. So yeah, so to get the better understanding, so you can log this thing like you can log this thing and try to understand how this dp array is building. So if you like let me explain this thing by taking this yeah. So like for this like this can be filled using this thing. So let's take yeah, this is a second one. So the for the one like for this you can see we also make the array for this thing. So it was look something like this, like 1 2 2 4 4. So you can see like 1 2 2 4 4. So yeah, we getting same thing because like in this you can see I have traversed right something like in row ways, and in this we are making something like I comma j comma I. You can see like firstly like in I we have value and in j we have something like 18 value. So yeah, in that way it looks something like that. So like in k equal to 1 step we can reach 2. So but if we can make 2 jump from I, what is the value we can reach? So if you can make 2 jump from 2 jump from I, where you can reach like if it's j become 1 in 1 like j is 1, then you can jump from like reach to firstly you can reach I comma j minus jump from previous jump, like something like that. uh if we have something we have to jump for 2 raised to power 4, it's going to be a like 2 raised to power 2 plus 2 raised to power 2. First if we can make 2 raised to power 2 jump for the current value, and then from that value we get again we make 2 raised to power 2 jump. So yeah, so that's we are doing, and after that like you can see like we are doing I comma j minus 1, and again we getting that value. From that we are again making a jump to get like dp of I comma j. So after that, yeah, after that our dp array is filled, then we are simply checking this thing. So I hope you like this video. If you like this video, please like and subscribe my channel. So thanks for watching this video.